Good afternoon. Welcome to the 17th technical lecture from NCTS. In continuation with the last lecture, a workhorse called green sand. Today we will be listening to Mr. Subramanian again on the subject of green sand in the service of creating good castings. Mr. Subramanian, with his vast experience of around 50 years in industrial responsibilities at Tata Motors and as an independent consultant, has attained a stage where we can refer him as a specialist in grey, HG iron, and aluminum die castings. With experience in almost all related areas, including foundry technology, process and quality system design, methods and tooling validation, projects, outsourcing, and energy conservation. He is also active in conducting training programs and seminars for foundries and authoring technical books and educational material for IF NCTS. With this, I now invite Mr. Subramanian for his address. Over to you, sir.
The last session we had was about how the sand got out of the mold and when the hot sand was moving around. So what all happened to the hot sand and how it was made fit enough for service again. So we went up to the mixer, and then today we'll take off from the mixer and see how good castings can be made thereafter. So it's a recap. From the last session. So this was a cycle of events with the green sand moving about. So we talked about the ambient zone and the hot zone, where the hot zone consisted of the pouring event and through the shakeout until it reaches the sand cooling and then it gets cooled. Thereafter, we have this ambient zone where the preparation takes place in the mixer and then it goes to the molding and then it is getting prepared for pouring once again at box closing. Now the point was in the ambient zone we are all comfortable, and then in the hot zone nobody wants to go near because basically the environment is not friendly. It's very hot, humid, and very dusty. So we don't really get an opportunity to see what exactly happens. Whereas we are busy counting the molds and then the castings fall in this area. So this is where we think that the money is made, the profits are made here. But really speaking, the sand does a lot of work. And when it is molded, it gives you the shape that the casting needs, and then the casting can be sold in the way that the customer wants. So we made the virtual tour from takeout onwards, because that's where the sand gets loosened out from the mold and then the casting is taken out. So we made a virtual tour, and from the shakeout, we went till the mixer. So now we will start our journey further from molding. We can say from mixer to the mold and then closing. So to start with, we'll have a review of the mixing process, what we discussed last time. Basically, all these inputs are there: return sand, cold dusting substitutes, the bentonite, which is a basic binder, some amount of fed sand, and an adequate amount of water to make it ready for making molds. Basically, in the mixer, we said it should be a very homogeneous mix, which has all the strengths which are required, and then they should be uniform. The homogeneity and uniformity are important. Then we said the bentonite should be activated. If it is not activated, then of course you don't get the strength. So this activation process, we also said it is not an instantaneous process, it is time bound. So it takes time to get the water into the bentonite layers. The moisture is controlled not only for the strength at the mixer, but also taking care of the losses during transit and the storage. And then when the molding takes place, we talked about compactability. One minute. Ah, sorry. Then it goes to the molding machine. We have some belt conveyors and some transfer points. In this process, there is a loss of moisture. The moisture that is needed while it is traveling to the molding line is this evaporating moisture loss that is obvious. The number of turning points, if they are more, then moisture loss will be more. And then if the distance between the mixer and the molding machine is more, then also the moisture loss will be more. Then the moisture is also required for wetting the bentonite, which is not fully activated in the process of mixing. So ultimately, what you require at the molding machine is a compactable sand which can flow over the profiles of the pattern. Then you require the molding machine should supply the energy for compacting. It could be jolting, it could be squeezing, blow, or any other energy supplying methods. The ultimate objective is to produce a rigid mold, which is measured by mold hardness. Yet it should be permeable enough so that you can get rid of air and gases that are generated inside while the coating takes place. Then the molding machine should also uh, satisfy that the mold is not having any cracks or there are no damages during stripping. The moisture and strength is adequate so that the edges are not spoiled. So these are the things we looked at last time. And we also discussed why the sand should be cooled and how cool is cool, we said. The around 38 degrees, everything is fine. But when it goes above 48 degrees, then the parameters gets disturbed. Then around 60 degrees, your molds are very weak and they become friable because there is a lot continuous loss of moisture. Then around 70 degrees, even in the mixer, you cannot mill it because water evaporates faster than you can get the water into the clay. So we'll start with the development of green strength. This is a familiar diagram that everyone talks about. There is, as you keep adding moisture to the green sand, the bentonite keeps absorbing and then it starts developing strength. When it reaches a maximum strength point, thereafter, excess moisture is going to drop down the strength. So initially, the position is like this. The sand grains are coated with not adequate moisture here. So when I keep adding moisture, then the bentonite has the ability to swell. That means the water enters the layers of bentonite and then there is a swelling because of OH ions entering the spaces between. And if the water is excess, then the water remains outside. It becomes a slurry. So in this, the absorbed water, if it is too less, then the strength will be less. If it is too much, again the strength will be less. What's important here is about 10 to 20% more moisture than required beyond the maximum. That is where we operate. We don't operate at the maximum strength, we operate somewhere here. This is called the temper point. And this is about 10 to 20%. It depends on the molding process and and the design of the layout from the mixer to the molding machine, the storage, whether you have aerator, whether you have too many bins on the way, silos. So the temper point is not a single point, it's always around hovering in a range. A mold determines the external features of a casting. Obviously, it is the impression of the pattern that goes into the mold, negative. But a mold is not a mold unless you can't compact it. You cannot have a mold which is not compacted. So the moment you strip out the pattern, it should not collapse. So you need a compacted mold. So we should talk about compaction to start with. Although it has strength, the sand, the strength is of no use unless we compact it. So the word that we should use is mold density, and even better, we should call it rigidity. So a rigid mold, what does it signify? What are the components of getting a rigid mold? One, of course, is a compactability, because you cannot make a rigid mold unless the sand is compactable. And if you supply energy, it should be able to get compacted. Then the compaction process itself, somebody should be there to compact it. You need an energy supplying device. Then the temperature of the sand. So we do so much control on the moisture required for molding. So if you don't control the sand temperature, you lose the water, and then it doesn't become compactable. Then the bentonite that is there should be activated. Only an activated bentonite, when it is swollen, it coats the sand grains and then gives the plasticity, enough plasticity to bind themselves to hold the sand in the system. Now we look at each of them independently. So the compactability means its ability to get compacted when compacting forces are applied. Compaction means that you are moving the coated sand grains under forces of compaction. This is very important. And then you have sand temperature. The loss of moisture due to heat from the sand grains is a very important factor. Sand coated with swollen binder to provide maximum strength. So the rigid mold is the basis for making a good casting. Now, how the compaction takes place? It's a very simple theoretical explanation. You have this sand which is in a loose form, and then the next stage they can be brought together in some kind of symmetry like this, and then they can be made even compact with a different symmetry. And when you add smaller grains, then the density of this compact increases, which means that you have more sand particles in the same space. And they also increase the number of contact points. This is an important factor, which is essential for green bond. The more sand contact points are there, the better is for bentonite to come closer to each other and then give a green bond. This is a 3D view. There are different shapes of sand: angular, subangular, rounded. But of all things, subangular is preferred. You don't get completely round sands. So the packing density changes with different shapes. That's obvious. When the sand is angular, it also has more surface area, so the binder requirement also increases. So these are the factors behind the demand for bentonite and the amount of moisture that has to be controlled with different shapes of sand and trying to get sand from different sources, it's good to know what shapes are existing in that and then what type of problems you can anticipate. And accordingly, you change your um, sand mix. How does green bond improve during compaction? Let's take the case of two sand grains which are coated but little apart, and let's bring them together and they touch each other. At this point, you can see that there is some contact point, and then the bentonite contact area is only this much. I go a little further and then bring them together. Let the sand touch here, touch each other. It can't go any further. At this point, you can see that bentonite has spread so much, so you get a contact area which is much larger. So obviously, the green strength, what we talk about, is this contact space, which is going to bind the bentonite here and bentonite here, and they form an envelope for the sands inside. So it's a free-flowing grains, uncompacted, it's well compacted. So you can have different molding machines giving different degree of compaction from here to here. So the choice of molding machine happens here, and the sand that you have to choose is within the foundry. Let's talk about an average grain size. What is an average grain size? So obviously the sand that you get is not going to have a single grain size. It will be having big and small, medium, everything. So you need to have a measure of what kind of average grain size that we can talk about. So the American Foundation Society has devised a method, universal method for defining this grain size. The average grain size is if you have a sieve of a certain dimension, if the average grain size passes through that sieve, then that is a size. So basically, you have some large grains and small grains, and then you can see some gaps here. And then if you add two small grains here in the space, then you get a classification of a coarser grain here and then a finer grain here. So what is the difference? The average grain size here it is more and here it is less. So basically AFS GFL is the terminology used. American Fundamental Society grain fineness number. It's a number. There is a method of calculation which I will not go into. It's a very simple way of doing it. A set of sieves are used and then you sieve them and different layers of sieves. You get different quantities of the sieved material and then you weigh them and then there is an arithmetic to go behind and then you get that number. Let's talk about the rigidity of the mold, which is in terms of density. Supposing you say density, you have measure of density here, low density, high density, low density, high density, low density, high density. For a jolting process, a squeezing process, and a jolt and squeeze process. Now let's start with it's just a schematic and it's not perfect. It is only to make a certain concept clear here. So in jolting, and here if you take a pattern plate and then the mold box top, so this is the height of the mold box, and the bottom of the mold box where the pattern is. During jolting, you get the highest density, and at the top, near the box top, then you get a low density. Whereas jolt squeezing, you are applying force on the top of the box. There is no force here. So obviously, the top of the box will have higher density and compared to the pattern area. And if you have both jolt and squeeze, you can expect somewhat a situation like this, where you get high density near the squeeze plate and then the high density at the jolting point near the pattern. And somewhere in between, you'll have a variety of strengths which are lower than these. Let's take this a little further. So the conventional jolt squeeze, we said like this. Now, when you have a high energy compaction, what we're trying to do is this region be converted into a more or less uniform density right from top to bottom. This is the aim. So that the molding machines will have any variety, anything from here to here. So that is a choice one foundry has to make. So let's look at the pattern itself. Let's say this pattern is having various contours. So we are trying to compact the sand around this pattern profile. And you can expect low density where the wall is almost vertical, where the draft is poor. Whereas in the flatter regions, you will get a higher density. This is a general pattern of hardness. If you check the hardness, you'll always find the vertical walls or the sloping walls have low density. The hardness will be less, and then the other areas where it is flat or very near the pattern plate, there they will get a higher hardness. So when somebody writes mold hardness in the data sheet, and then you want to look at it after a month, and then what was the mold hardness value, one has to know where he has measured it. And you may start getting rejects because of low density areas. So the actual reported value might be this, not this. So you should be able to understand this variation in the pattern. Let's look at this picture once again with jolt squeeze. Let's try to understand if you have only jolt but no squeeze. Sorry, if you have a jolting which is not adequate but squeeze is adequate, that means squeeze is almost same, but the jolting has not done its duty, so it is giving a low hardness, low density. And then how does it translate into the pattern? It gives a low density area here throughout. So in your pattern region, you are likely to get a softer mold because of poor jolting. Say for example, if you have poor squeezing, but the jolting was good, the situation is here, you get a very good compaction in the upper zone, whereas near the pattern, you are having a poor compaction, and this is likely to give you stripping problems, or when you put the cores inside the mold, it might damage the mold, or during transport of the box, or there are any jerks on the pallet conveyor, then all these problems will arise. So basically, to understand this only, this diagram is good. Let's look at some reasons for mold breakage. This is not exhaustive, this is just a primer. So one can look at failure modes, so, and then put up a control plan accordingly. Basically, mold breakage can come from the pattern or the sand or the molding issue. So here are three sources. We are not putting any people's problem here or any other maintenance issues. So we'll take one item here, pattern. So the mounting of the pattern makes a big impact on how the mold is going to be stripped. And if there are undercuts in the pattern, then obviously they have to be taken off during the initial pattern design, or if it is developed during the process of manufacturing casting, you need to understand such undercuts are developing, then you need to take action accordingly. Then if the draft angles are not adequate, then also it might give a problem. So this is compounded with the molding machine issues also, because if the molding machine is not going to strip very parallelly, then even the draft angle that you have given may look inadequate. The next issue is about the green sand quality itself. The strength of the sand, obviously, that is a basic requirement. Then we said about compactability and temperature. So this constitutes green sand quality. And then the molding machine. So here the compacting ability, that is the energy that it can supply, and the alignment of the machine. And then the operating methods. So how this operating methods is a big subject by itself. So you need to clean the boxes, you need to clean the pallets, you need to clean the pattern before every mold. Beyond this, there is also the upkeep of the molding machine efficiency. That is, it should uh, it should it should work itself for giving the pattern the best reproducibility in the mold. So let's get into the casting defects. We need to understand some origins rather than discussing about the defect. We will discuss why some defects happen, and before the why, what uh, basic issues are there in the sand which contribute to the defect creation. If you know that, then solving such issues become much easier. We look at sand expansion defects. So now the defect by itself, the name is not sand expansion. The defect will have some other names. We'll come to that. But the reason for such defects is the expansion of the sand. Obviously, any material with heat is going to expand. That is a fundamental rule. In our case, when liquid metal is poured at 1400 plus temperatures, the sand is very close to the metal surface, is going to be impacted with that heat so much that it starts expanding ferociously very close to the metal, and then just behind, because of the moisture, it is going to absorb some heat, and then relatively less expansion will take place towards the inner part of the mold. You know, the phase that is close to the casting phase is it takes the brunt of the heat, and then that is going to expand. So if it expands, obviously you can understand that it is going to collide within itself. That means the grains themselves are going to expand, and then all the grains will have some impact against each other. So then there is no space for them to expand. There is no free expansion space available in the compacted mold, especially when you compact it for very high densities. A good machine, very high energy compaction. The surfaces will be very, very hard, and the expansion possibilities are limited. So to understand expansion, let us look at this curve. These curves are not um, exact curves. These are only schematic, just for explaining the principle. So we have different varieties of refractories. The general use is silica. We have this olivine, chromite, and zircon, which are air refractories. So the curve shows one important factor, that the expansion itself is minimal, and the change that takes place over a range of temperature is not significant in terms of zircon, and it is more significant in chromite, much more in olivine, and in silica it is very, very obvious. But of course, you don't. see it when you're pouring the metal, but then this is what is happening inside the mold. So the thermal expansion, this is a linear expansion of sand in percentage. It's given against the temperature in degrees centigrade. So somewhere in this zone, you see some disturbing factor in silica sands. When you pour metal around 1400, the actual temperature of the sand is somewhere around this, even higher. But by the time it cools, generally it is here. And then if you see, this line represents the peak value of expansion across various refractories. And then this shows that the higher the refractoriness, the lower the peak goes. So the mostly used silica sand is the worst sand, but still we want to use it. But understanding this is important because any defect related to expansion is due to this. Now the silica, what we use in foundries is not a pure quartz. So the silica has the properties of quartz sand. In what way? To plot this silica sand and overlap it with the quartz behavior on the same expansion versus temperature relationship. You will see that there is an area where this rise in linear expansion is so sudden, it's almost vertical. That's a place where the first crystal relationship, alpha quartz, converts itself to beta quartz around 573 degrees centigrade, and it is reversible. So you lower the temperature, it becomes alpha quartz, and you raise the temperature, it becomes beta quartz. What's important here is there is a slight change in the crystallographic structure, but not entirely. But when that happens, the expansion is almost infinite. And thereafter it plateaus. Now, it looks like this. The alpha quartz has some kind of facial structure like this, and then the beta quartz has some kind of structure like this. So around this 573 degrees centigrade, there is a continuous change. Whether it is high or low, there can be change in the crystallographic structure. They say it is irreversible. Sorry, it is reversible. It is trigonal symmetry, and this is hexagonal symmetry. So let's talk about the facts that's happening in the mold. You heat the sand. Heat the sand means what? How much heat? So we talked about expansion. If the heat is more, it starts fusing, that is fluxing. And a later state, it may disintegrate because of chemical changes in the sand. So this is an extreme case, and then we will stick ourselves to the expansion part, which is the earliest stage of sand expansion, which is taking place at the mold surface. What happens during expansion and what is the result in the casting? There are various types of defects that are utilized, that is the terminologies which are utilized, and you'll see all of them, but you will also notice that most of them are not being utilized in Indian context. We are only familiar with a couple of them. Fins. It is not casting fin, it is a fin that is developed on the mold surface. Veins we talk about. Rat tails we don't talk about. Buckles we don't talk about. Scabs, yes, we are too eager to talk about scabs. Drops, we don't use drops, we say sand inclusion. Dimensional issues, we don't relate it to sand at all. This is another problem. So CAB is the easiest word that everyone wants to term as, but many of them are not scabs. The terminology, the people who are trained on the shop floor, unless they are made aware of what scab is or what a buckle is, what a vein is, they will not be able to report it correctly. All these things happen not just because of sand is expanding, but a poor clay bond is another culprit. So even if the expansion takes place, if we had a bond which is much better, then there is a good chance that you won't get this defect. You will see that a little later. So it's a combination of both, heat as well as the clay bond. So the progression of this expansion defect is, one is starting with a vein, then it becomes a rat tail, then it becomes a buckle, then the extreme case of sand defect is scab. We'll start with the rat tail. It looks somewhat like this. It's a minor buckle. So the next stage is buckle. So the expansion has produced a fine crack on the surface of the mold through which the liquid metal has seeped inside. So you can see the metal has seeped inside. And in the buckle, it is much more pronounced compared to the rat tail. So when the surface sand passes transformation temperature, a scab defect forms. This is the next stage. We'll talk about scab a little later now. A scab looks like this in plasmics. Whereas an erosion, there is an expansion scab, there is an erosion scab. You should be able to distinguish between these two. We'll again explain this a little later. These are just pictures. So we talk about expansion scab. So expansion scab, what we say is the sand is expanding and then it is producing a scab. So now we have the sand mold here and then the liquid metal here. There's a space above the liquid metal, it is radiating heat. So the sand here gets warm and then hot during the filling event. The metal has not reached the surface of the sand, it is still rising. It is during the pouring process. So now what happens? Now the buckling stage starts. The radiant heat from the flowing metal starts heating the sand layer, and then the surface here starts expanding because the heat is too much, and then it might be passing through that alpha beta transformation stage, and then it is expanding quickly. So then you develop a buckle because sand cannot remain in that position any longer, so it starts buckling. So when the buckle is developed, a void is created behind. Because obviously, what is a buckle? Buckle is a layer of sand which is coming out of the basic sand mold. So when it is coming out, there is a space created. In this space, there is a rupture taking place. That means maybe one rupture, two rupture, three ruptures. Basically, this sand which is here, which has buckled out, has become so dry, it has shrunk and it doesn't have the green strength anymore. So it doesn't have it. It just starts giving out because there is a tension created in this mold, and then due to the tension, it cracks. It develops cracks. The next stage is you start filling the metal further and further, and then you have reached this point. Now at this point, it starts filling that empty space behind. The green space is the empty space. That also gets filled up because through the crack metal enters, and then you have a void space filled with metal, and finally you see a metal which is stuck to this casting through these small cracks, and then there is a layer of sand in between. which is stuck. And you try to remove this piece and then you will get a cavity in the casting. A scab defect in the solidified casting covering a layer of sand. The yellow part is a layer of sand and this is the scab defect. So if the scab is ground or chipped off, there will be a depression in the casting. So it is obviously a destructive form of finishing the casting. So you should never have this kind. So it has robbed the surface of the contours and the dimensions that is expected in the finished casting. Let's say even if it is in the machining area. So if it is exceeding the machining allowance that is given here, then you are going to have an unmachined patch here. No, the other issue is we talked about crack here. What happens to the sand which was there? The sand which was in this space simply falls down and then gets embedded inside the casting. So invariably you will see a scab defect associated with some inclusions of sand, the space behind. And sometimes if it is a wall, you may see some sand inclusions on the other side of the casting. Whereas you have a scab in the zone where expansion has taken place. It can also happen at the bottom of the mold. What we talked about was the expansion scab in the upper part of the mold. This is due to radiant heat, upper part. Now we are talking about bottom part of the mold. That is, drag mold also can have scabs. This scab is again the same, similar situation. You have this mold, the metal is there, and the metal is heating up the surface of the mold, and this layer is expanding, and then there is no place to expand further, so it curls out. It just opens out, and then the metal enters. You can have a scab. Consider both. This is the top scab, and this is the bottom scab. Now we want to explain a terminology called wet tensile strength. See, all the other sand testing procedures like green strength, green shear, green tensile, green shear, or any other bending test or collapsibility, all are done in the laboratory. Sand is at ambient temperature. What happens during pouring the metal is different from what we test in the green state. And this wet tensile strength is measured in the lab again by heating the sand sample. We will not go into the testing method, but we will just understand what is wet tensile strength. So you will see that the hot layer at the metal face transfers moisture to the layer just behind, making it wet due to the excess moisture. What is happening is there is a condensation zone, which is a wet layer. This is a hot metal here, and then this top layer, and in this case the bottom layer, becoming dry. While it is becoming dry, the moisture is escaping to the layer beneath here and layer beneath here. So the water is escaping towards the inner part of the mold, and this water can be as much as 3 to 4 times the water that is initially in the sand. So it becomes so wet. And secondly, because the heat, this water which is there, it is going to be at near boiling point, almost near 100 degrees. And then sometimes it might split also to oxygen and hydrogen. So basically you have a layer of sand which is having excess water. And we saw in the strength development curve, when there is excess water, it becomes a slurry. So a slurry is what it doesn't have a good binding strength. So the wet layer is going to have a very poor strength. So the expanding hot layers of sand creates tensile forces in it. That means when it is expanding, it is creating tensile force in the wet sand. That tensile force, if the bond is weak, detaches from the hot layer, allowing hot layer to curl or crack. This phenomenon of curling or cracking is because the weakness. Then the metal seeps through that, and then you create a defect here. You now look at another defect formation, metal penetration. I have seen in many foundries they use the word SF. SF is sand fusion, but actually fusion doesn't take place at all. So it is called sand fusion. Let's use the word sand fusion only, but basically it is metal penetration into the sand. How does the penetration take place? Basically, the roughness of the casting is the reflection of the texture of the sand itself, primarily, yes. But when it is deep, then there are serious defects. So you have a rough surface, you can say that it is related to sand texture. So very often one talks about rough surface and say that what is your sand fineness? So how do you control the uh, grain size of the sand, grain distribution? So that is at one level. If you have a mild penetration, then you find that your fettling operations will be a problem. So you have to do short blasting twice, or maybe ask to do some grinding operation where it is very poor. In a severe case, you can get what is called a burn on or burn in, where some fusion takes place. So these two can be a mechanical form of penetration. This is a chemical form of. So what are the issues here? One is the sand. So you look at the grain fineness number, deck fines, compactability, volatiles, oils, etc. In the mold, if the compaction is poor or venting inadequate or the moisture is too high or some nails and chaplets are disturbed, method due to turbulence or fill rate is too fast or the glating system is incorrect, then also you can have some. These are uh, creations of some explosions inside the mold where there is pressure created and then you have penetration, which is severe penetration. You can also have problems with cores, the moisture in the core, the binders that are used, or even the coating which is not dried completely, or venting in the core is not adequate, so the burnout of the resins from the core is entering the mold. Or during pouring, there are a lot of issues. Metal, the temperature of the metal, and how fluid it is. The pouring means you spillage. The spillage means you are pouring. If it is not controlled, there could be metal overflowing from the pouring cup. Simply looking at the uh, grain structure in the mold, you have a bentonite which is swollen and then they are in contact in the compacted mold. And then as you go near a liquid metal, then the moisture escapes, so bentonite shrinks, and then there are some gaps. And very close to the metal, there is a lot of gap, and then the metal can enter through the gap. So moisture escapes and then shrinks a clay envelope, thus creating gaps between the sand grains. This is one type of roughness. The silica sand adhering to the casting surface. If the pressure from gravity and mold explosions assisted with fluidity allows the metal to seep through the gaps, then it will grip the sand. So it will be difficult to remove this sand because then you'll have to grind off this much portion so that the grind because metal has entered up to this point. So this is a moderate penetration. This is one layer. So you may account for certain loss of surface wherever this situation is because this much is a sand itself. So this is a casting surface. So while grinding it, you might do some excess grinding to ensure that there is no sand left over. But nevertheless, the surface is going to be a blemish, and it's not acceptable for any aesthetic requirement. And if it is very severe, then it is going to go to the next level of grains also. This is a schematic, it may not be exactly like that, but just to explain the principle that a severe penetration might look like this. We need to remove all this sand. And it doesn't mean that sand is going to remain here. When this happens, as we said that bentonite is shrinking, there is no more bond. So if the force is so much, then some of the sand grains can get dislodged from the space and then it get included in the casting itself. The severity is not only the compaction, but the bentonite quality and the compaction and the other factor that we just now discussed, which is creating these explosions. An example of a soft mold which is penetrated is here, and then it is an explosive penetration which is all over the casting. Another example. Basically, if you cut the section across this casting, then you will see a sand layer which is stuck on the casting. This is the casting area, and then the metal is held on to some sand grains, and then the sand is stuck to the casting. We talk about another defect which is peculiar. Not everybody will be having this, called the fish eye defect. Casting, ductile iron casting is having this fish eye, looking like a fish, eye of the fish. This is because of the use of sleeves which contain fluorides. Fluorides are added in the exothermic sleeves to help ignite the aluminothermic powders quickly. You need to create heat fast. So fluorides are added to hasten the process. And when the casting is shaken out, there is a residue from the sleeve which gets mixed with the sand. So when the return sand comes back to the molding, it will have still some pieces of or some powdery stuff of this fluoride. These fluoride particles might still remain inside the mold, and that, assisted by moisture in the sand, can give this kind of defect. I'll not go into the creation of this defect, how it happens, but it's enough to know that it is there. So fluoride-free exothermic sleeves are the solution to the problem, but it's not always to ensure that these sleeves are completely burnt, because when a sleeve is molded in, the one part of the sleeve is exposed to the hot metal which is inside, whereas the outer surface is in contact with the wet sand, so moist sand. So it doesn't burn out completely in many cases. So there will be always some contamination and there will be always some residue left. So best is to use some fluoride-free exothermic sleeves which are available in the market. The fourth issue that we can discuss is about inclusions. So obviously we have to exclude all the inclusions in the casting. So what is the origin? There are many origins. They are very simple, but these will help in making the Ishikawa diagram for control plans. Basically, we can start with the molding. So we can have compactability, compaction, packing. We have to look at all these areas which are causes for sand inclusion. Sand inclusion means sand is not in the mold but inside the casting. So it has come out of the casting, come out of the mold. So what are the various reasons? Pattern clearing, stripping, misalignment, box jerks, palette cleaning, box cleaning. Palette cleaning is worth mentioning here. If the palette is not clean and you are keeping the mold drag box on the palette, then a lump of sand will crack the mold on the bottom. So then the surface inside is cracked, and then some part of the mold is made loose. So when the metal is poured, sand can get dislodged. assemblies. I will not read out all the things, but it is enough to know that these are all the causes. So while keeping nails and chaplets and washers, you can dislodge the sand. So when keeping the filter, the size control, filter size should be exact because you have made a cavity in the mold for a certain size. If you keep getting the filter from 3, 4 sources, then you will have different dimensions. Placement, cleaning the filter before placing, venting, screw cutting, these are other issues. After vent piercing, you will see some sand is stuck in the hole, and then when closing, the sand falls inside the mold. There are various ways in which this kind of sand, loose sand enters the mold. Cleaning, while cleaning, you think that you are doing air blowing, but then the sand keeps rotating inside the mold itself. Or while you're cleaning one mold, the sand is flying into the next mold which is already clean. So these are very pathetic issues. Then during closing, the push pin wear out. The closing is not parallel. While clamping, some people use hammers to clamp it. So during that process, some sand can get loose inside. These are all very simple and obvious process errors which have to be taken into account. And beyond that, a faulty gating design is another contributor to the site. We'll see one example later on. So the casting is getting rejected for scab or some kind of sand defect. Okay. And you found nothing exceptionally wrong with the sand that seems to bother you. It means that you find that your controls are very good and your data shows that there is nothing really um, really uh, really the reason for that kind of scab or some scientific. Now we'll see some examples and see how to solve such problems. We have seen these examples in a lecture before in troubles in troubleshooting, but we'll take those couple of examples here to reinforce this concept. So the leaking gear case, location of the leakage was always the same. So there was a particular place in the casting which was leaking, and the analysis showed inclusions of molding sand. So this much is very clear. Everyone knows that it is sand because the sand is included. There is a connection between the oil inside and the atmosphere outside. So there was leakage. The data and sand parameters had nothing unusual to say. They were combating two issues simultaneously. One is the shape of the casting and then the size of the casting. They always found that the top side of the gear case was having a tendency for cold metal defects. And then leakage is the second issue. So if you do anything for leakage, it should not disturb the gating system, otherwise you will land up in cold metal. So both things have to be lifted simultaneously. So what was missed, although the sand was good, they missed the main point. There was an erosion of sand at one of the inlets. We will see how it happened. So this was the gear case, and then the top surface had a cold metal tendency. The current gating system what they had ensured that there is no cold metal. But they had another problem because there is a soft mold here. It's a vertical. We have discussed this. Vertical wall has low density mold density, so it is a soft mold. So whenever chance is there, either an expansion or a jerk or any metal passing at that point, there is a likelihood of some sand getting dislodged from here, and then that was getting included here. Oil leakage due to sand inclusions. But there was a sand erosion at the inlet which was not noticed. So they were just while grinding off the parting line fins, it was just ground off and nobody noticed it, in a very close observation. So what happened? How did they solve this? They made this change. They removed this ingate. The sand erosion was happening at this ingate. So this ingate was removed, and then the area of the ingate was shared by these two adjacent ingates, and then they were made inclined. The inclined because you had a cold metal tendency at the top of the zone, so you need to send metal to the cold metal area. So you have to direct the metal in this. Yet you should not have any sand erosion. So to avoid the sand erosion, the ingate was removed from here. So the problem was solved. There was no erosion. There was no leakage. Neither they had any cold metal. Another example is scabbing is not the fault of sand. So we have been telling this scabbing is due to sand, expansion of the sand, and then the heat, and then the binding forces, whatever. But here is a case where sand is good, but scabbing is there. Flywheel casting suffered from scabbing tendencies and sand intrusions on machine piece. That was the problem. Nothing was noted in the data. Fully machine casting had no traceability. This flywheel casting gets machined completely. So after machining, you don't come to know how the layout of the casting was there inside the mold. It's a multi-cavity pattern, so you need to know which cavity it came from and then how it was oriented inside the pattern. So the missed symptom was that the scab was always in front of the single gate because there were not any traceability. They could not locate this issue that there was a single gate, and in front of that gate only the scabbing took place. So see, this is how the layout looks like. There are 4 castings in the layout, and this is the primary runner. These are the ingates, and then this ingate in one casting is shown here, and then just in front of the gate there was a scab defect. Now obviously it is a classical scab defect. There is an overheating taking place because one location only the hot metal is entering. So the entire casting, this portion of the sand which is in contact with the metal is going to get overheated. So this overheating causes uneven expansion. This part of the mold is going to expand, and then obviously you are going to have some defect which is due to the expansion. Maybe it started with a buckle and then later on it developed into a scab. How do you solve this problem? 2 things were done. One is the ingate was split into 2 parts and then they were made inclined. With the result, the metal was not impinging at one location, but it was rotating. So the added bonus here is the metal was uniformly at a uniform temperature always, and the sand which is in contact was also uniformly heating up. So the expansion is not concentrated on one single location, but expansion was taking place uniformly, and by the time casting is filled, the expansion is not so significant that you can get a scab. So the circulating metal resulted in no overheating. So this is how the layout looks like. Each cavity had 2 ingates which are inclined. So we see that the scab defect is not solved by doing anything to the sand, but it was the gating system. If one says that your sand is rubbish and you can't solve the simple repetitive sand defect in the casting, look carefully. Sand is an idiot. Not all that smart to find the same place all the time. There could be other sources within the mold pack, not the sand alone. The mold pack means inside the mold. It could be gating system or it could be any other part of the sand, which is not the sand itself. Good luck and have good castings from the sand system. Thank you.
Formally thank Mr. Subramanian that all Shopful persons were aware of the concepts, but many concepts were known, but the theory behind them was not known. And this was explained very nicely with help of graphics, and the case studies explained the concepts further. Yeah. So thank you, sir. Thank you for a very nice lecture in which was understandable to even the lowermost shop floor person. Thank you for all. Thank you for attending the lecture to all our attendees. Thank you.